Based on band theory, we are classifying them. Okay, this is for insulator. This is for conductors. This is for semiconductors. So almost I think some crystal lattice structure, what you studied in chemistry, no? Just a broad view of that is what we are going to place it here. Okay, this is called as conduction band. This will be conduction band. Conduction band. So the energy gap, this is around 1 electron approximately. The energy gap, this is around 7 electron. So this is also called as forbidden. Forbidden means not permitted. If you look at the for conductors, it will be overlap. So what are these bands? Next question comes like, what are these bands here? Okay, let's. What are the semiconductors? A good example of semiconductors are silicon, whose atomic number is 14. Next we have germanium, whose atomic number is 34. Let me take the silicon example so that I can draw a few number of electrons. So if you look at the atomic structure of the silicon, it will have right silicon. So how many that if I go for distribution, then 8 electrons. Then outermost orbit will be 4 it will be there. This not, yeah. So these are the any questions they may ask you. So let me just show this also. Okay, these are for silicon atomic number 14. So if you look at the 1s, so shall we put like this? 2s square, 2p6, 3s square, 3p square. These are the shells. So now what happened? I think we have reached more advanced atomic structure, not Bose atomic model. We know now modern atomic structure. From the modern atomic structure, from that what happened? From Pauli's exclusion principle, all everything based on that. These are the levels. What happened? Orbits like a 1s is one orbit, 2s 2p is one L shell, and 2s 2p. This will become subshell. Then 3s 3p. So this will become subshell. So like that, what happen? The will divide in each subshell. What happen? Will place electrons like a 2 electrons in the shell 1s, 2s again there, 2 electrons. K, I think this will be K shell, L shell. This will be M shell. In M shell again, it will be 2 electrons. That M shell is what we'll write it here. So since let's begin the way when we learned few ideas, no. The subshells is what we show it. Now this is for like a one silicon atom. We show diagrammatic representation. This one. Then for this is what I drew is this is for total substance, not for one atom. For one atom, you don't get that one. Means for one atom, for one silicon atom, the structure will be no, this will be 1s, 2p, 3s, 3p, 3d. So here how many states are there? 2n states. Here 2n states. Here 6n states. So 2n states and how many? So shall I put like this here? State. These are the states. Means possible locations. No, the electron, okay, it will be filled up, occupied by this. There are 2n states are there. There are 6 states are there. Here 2 states are there. They're filled up here. Here 6 states are available, but only 2 are filled up. This is what happens in the silicon atom. Is it okay? 6n states. What do you mean by 6n? 6 states available. In that what happens? The 2 are filled up. This remaining 4 are unfilled here. If you go for the crystal lattice structure, no, this is for one silicon atom. Like this, if the silicon atoms, if they come together, and so it's a covalent bond will be formed with the adjacent silicon atom. Like this molecule will be formed for the total substance. When I plot this for total substance, the band structure will take shape like this here. Yeah, we have box here, no? You can draw a few more like this. Okay, now come for this one. So when for total silicon substance, so these are the instead of lines, why I'm showing the boxes. This is the first question what you can ask it here. Now when the two atoms, if they come together, then how do they form? The energy of one will slightly increase, the energy of the other will decrease here. Like that, the energy of this one what happened? I think in one, so to make you understand, it's not there in book, but actually practically there's a logical way what I can show it for. If there are only two silicon atoms, but we never see in practice only two silicon atoms. Usually it will be crystal lattice structure. This is last third diagram is what only just to make students to think. I brought it. So this is the two silicon atoms. Let's assume that one. Two silicon atoms only for understanding purpose. So what will happen to the states? So this is the of silicon atom 1, 2. Like that. So what happened? The energy of one will decrease, energy of line. What is this dotted line? The dotted line is this one. They actually for one silicon atom, the energy of one will increase, whereas the other will decrease here. So how many states are there here? Again, you can fill up like this. This will be, see, so this is 1s, 2s, 2p, 3s, the 3p. The third diagram, it's not there in book. We are not supposed to show also, only to make you to think. And let's assume that only two atoms, if they come together, then the energy of one atom will increase, the energy of other atom will decrease, and this will be the average energy of one atom. It is there, no? What will the average energy? That will be energy, that one. So what is this K shell? This is like a K shell, no? Go back to hydrogen atom. We used to draw one line. It is for one hydrogen atom. For a sample or for two hydrogen atom, the energy of one atom will slightly will increase, that will decrease. On and every, the energy of one hydrogen atom will be somewhere here, will be average of that one. So like this for two atoms we can show it. Now I am just bothered about this 3p level. 3p level, in 3p level, if the two atoms, if they come together, how many total states available? 12 states available. In that what will happen? The two states of the one atom, atom 2 will be filled up, the two states of the atom 2 will be filled up. But practically what will happen here, the situation will be in either way. So what is that? When the two atoms, if they come together, no, so the two atoms which are here, no, the two filled states open, they will occupy here, and the remaining, the two unoccupied will be sent here. They will not be like this, and there'll be redistribution of states as well as the levels will occur. So let's not go to that quantum level or that band structure of in detail, that one. So if I just draw for two atoms, the two atoms what happen? I should not show that one. So what will happen to this A1? The two filled states what happen? They will occupy here, and the unfilled state will come. This is the rough way of analyzing thing. So here, so let's come for this one. So how many states are available here? This is called as 1s, 2s. This will be fully filled. Next, this will be 2p. This will be 3p. So what will happen to this 3p? The 3p only will split up. the 3p only, this together only is 3p. This will become 3d. The 3p only will split up. So here what happened, we'll get a fully filled up. This is. And this is made up of unfilled states. So when two atoms come, so this will not be like this. So what actually will come? So will take place like this here. Okay, this is the basic arrangement. This one. Why that band? Why that band? Why not one level? Like that for three atoms. I think for three atoms of silicon, if they come, so this oneness what you are going to show like this. If the four atoms, if same oneness, this is for three atoms. This is for four. If five atoms, six atoms, if there are n number of atoms for a total substance, so the oneness of all the different atoms what happen? Of one will be more, next what happen? This will be the average. This is the average. Of one of the atom will be more, one of the atom will be less. Like that, what happen? A band structure will be formed here. All these are called as the valence band. From here to here, this is called as a valence band. All these are called as conduction. Conduction band is not only one. Why that conduction band is having unfilled state from where to come? So did that thing like. So all that particular two states are there, no? So what will happen to this 3p? The 3p will get further subdivided. Will get further subdivided where the two states will happen, each atom. So like each atom will contribute two states for this. And because of that, what happen? We'll get here like a fully filled, like a uppermost valence band and an empty conduction band. We say empty in the sense like you can see that one here. So this will just go and occupy that one. So now shall I say this 3p is what? And what I wrote semiconductor. Let's not bother conduction band. I'm bothered. We say forbidden. No. What do you mean by forbidden? Why that word is used? Forbidden gap. This one. It is not permitted. Either electron can exist here or here. It cannot exist here. The forbidden means not permitted. So is it possible to locate any electron either here? It can see if I supply energy, what happen here fully filled. Here will have valence electrons here, but it is a fully filled. We don't have any vacant state. Here, what about here? All the states are vacant. If you supply energy, what the electron can jump from fully filled to unfilled state, or from valence upper valence band to lower conduction band. It cannot be here. So therefore, that forbidden gap is what is this one. So therefore, we say forbidden gap. So the lowermost unfilled, the lowermost conduction band and uppermost valence band, what it is 3p only of the silicon atom for silicon substance. The third diagram, it's not at all a thing only for students to make think I brought it. Otherwise, I should show only for atom and for substance, because we never discuss anything for two atoms. And this two atom thing what happens should not be correlated to this also. Only for students to make think. When I'm posting it, I'll erase this. When I'm sending as a PDF, no, I'll erase this because nobody, which particular intellectual person has drawn this, people will question me. Only for a understanding purpose. Okay, got this one. So why that bands are formed? The discrete energy levels. So what is a band made up of? So what is a band? Bands made up of, shall I say, discrete energy levels? What is the valence band in the made up of that one? It's like the discrete energy levels of specific energy levels of an atoms. So there is nothing but the valence band here. So this is nothing but the uppermost valence band, fully filled. Lowermost conduction band, we do get plenty here. I'm not showing that. We can just go on add, no, 3D. Next again, you can keep on add conduction bands. So what are conduction bands? Empty conduction bands, because they'll have unfilled state. And what about the valence band? It is a fully filled here. So if you want to further accommodate one more electron, there is no state available. See, it's as good as like how many electrons you can accommodate here? Only two, no? No, sir, I'll place one more. this structure will not permit, this atom will not permit. Are you getting now? So what about valence band now? So valence band is fully filled. It is not having any further place. It's like as good as like a, for in classroom, no, first bench. Omni, I think will sit four, no, in our, I think, yeah. So what is the number of states? Number of students can sit four. Four students are sitting. One more student wants to come and sit. Not permitted. The bench will not permit. The similar situation is what happens here. So what is the valence band? It is having all states are fully filled up. And what about conduction band? All states are empty. So we'll say unfilled states. And valence band fully filled state. So here valence band means not only one. All these are valence bands. The uppermost valence band and the lowermost conduction band is what we are taking for discussion. Similarly, for conductors, what happens? Such a situation here, they'll overlap. Conduction band, valence band, and similar. And what happened to the insulators? The gap will be 7 electron volt. For insulators, this particular energy gap will be 7 electron volt. Again, you can see like a, sir, like a, let me take germanium. I think for germanium, we should not discuss at 3p, no? Where do this forbidden gap will come? Will it be at 3p? I think you know enough atomic structure. You have to go further, no? For germanium, it is 34. So start filling up. Here 6 states, 6 will be filled up. Like that, you start filling up. There again, you'll get forbidden gap somewhere here. Like that, based on that atomic number, the forbidden gap will come at different levels. Not only it should be here only at 3p. For germanium, it will not be at 3p. Forbidden gap will be somewhere. So what is a band? What is a band? It's a discrete energy levels of different atoms of a substance. One specific level, what happen, will form a valence band here. So this is a lowermost valence band, this is a uppermost valence band, and this is a lowermost conduction band. This is a fully filled up, this is a completely empty. This what, like this, we classify the metals or solids based on, or we classify the solids based on this band structure. So I'm more interested in this. Already we have studied in current electricity and this of no use. We are going to study this like a semiconductors here. What are the semiconductors? We have germanium and silicon. These are the primary thing. So we'll look at the structure here. So what is the silicon? Actually, if you see the atomic structure, if you look at the silicon substance, there's a diagram more popularly will be using almost at many places. No, you can. So that it is like this. Huh? Now come for this. So this is silicon atom. It's a tetravalent atom. Outermost 4 valence electrons. It will share its outermost 4 valence electrons with the adjacent silicon atom and it will form a covalent bond. Now what is the dot here? Black dot, valence electron. I think we'll continue with the same symbol. And how much of energy you should supply to break up this covalent bond? 1.1 electron volt or around 1 electron volt. For silicon 1.1, if it's germanium, it is 0.7 electron volt. Now why there is 0.1.1? The 1.1 will come, this one, when I go and measure practically, it is coming around 1.1 electron volt. For germanium, it will come somewhere here. And it is 0.7 electron volt. Getting the idea? So there's a way of describing this band structure. So this is silicon, like a structure what we show it. It is a tetravalent atom. So outermost valence electrons will have 4, outermost orbit will have 4 valence electrons. It will share with adjacent atom and it will form a covalent bond. This dot E, the dot represents valence electron. Okay, let's get into now the silicon, this atom. Now let's me just vary the temperature of this. I'll vary the temperature. So if I vary the temperature, then the valence electrons which are present here, if they gain sufficient energy, what happen? Due to thermal agitation. So what do you mean by thermal agitation? If I increase temperature, the atom starts vibrating above their main position. Due to that vibration, the outermost valence electrons, if they gain sufficient energy, then what happen? They will jump to the conduction band. So how much of energy needed? 1 electron volt. So what all you rise the temperature, the thermal agitation should occur. Due to that thermal agitation, the outermost valence electrons open, they should get sufficient energy to jump to conduction band. So therefore now, as you increase, as you vary the temperature, so what will happen? So some of the electrons from the valence band will jump to the conduction band. No, so this is a thing. So practically what will happen if you look at the silicon, this one. So practically what will happen? So some of the valence electrons will jump to the conduction band. So here what will happen? We'll get a vacancy. That vacancy I'll show by blue color, and the electron, it has become free from the atom and it will become free electron. So therefore, how do the so there's a conduction band here, some free electrons will be there practically at room temperature. Now I should not show many. Okay, we'll show few, and there'll be holes. Now the first time I'm introducing to the idea here. So what is a dot? Dot is valence electron. What about star? This is like a free electron, not center of mass. Free electron. And this bubble in the books open, they just show circle. So there's a hole. So first, like there's a conduction band. Oh. And we never show valence electrons in conduction band. That's the one practice because we are not bothered. We are not bothered about these electrons. This is energy gap, say like around 1.1 electron. So silicon substance at room temperature. Basically, they should not empty conduction band should be there. No, why do these electrons will come? Due to thermal agitation, what will happen to atoms? These silicon atoms, they'll vibrate. So when they vibrate above their mean position, so outermost valence electron, they gain sufficient kinetic energy, they'll get sufficient kinetic energy, and they jump to the conduction band. If they possess more energy than what is needed in that particular state, so they'll jump to the highest state. So like that, and now this particular thing is not binded to this atom. It is free to move inside the material. This is called like a free electron. The vacancy created by valence electron in valence band will become hole. So what is a hole? How we define? Vacancy created by valence electron in valence band is called as a hole. So what is the charge of it? It will be positive. But so like a electron not there, then free electron means all here electron is there. After some time it will move. No, here all will not come. So you see like there's a void. So in books, some books they call like a void. Void means like the vacancy created by valence electron in valence band is called as the hole. But sir, you never discuss something in current electricity chapter. S in current electricity chapter. So what actually happened is for a conductors. So we know that at room temperature, the electrons will jump from valence band to conduction band. Why not holes? You see that it has overlap, no? For conductors, what happened? The valence band and conduction band will overlap. So what all that holes that are formed immediately will be filled up by the same other electron. Suppose the electron jump from here, hole is created. This electron, when it is moving, you come and fill up. So like that, the probability of finding out hole in conductors is 0. So we have to discuss everything here probability, not like, sir, I saw, so just now I saw. No. What is the probability? 0. What is the probability of this one? If any electron jumps here, so sir, again, why can't this electron can come? No. The electron will be wounding in this conduction band only. Means, so what actually happens is, practically what happens, this electron will be wounding here. Sir, any probability of catching it? Yes. If it by chance, if this hole capture this electron, so finally what happens? Somewhere what happens? The energy should be conserved. No? So this electron will get sufficient energy and it will jump out. So like that happen, the number of holes and number of free electrons in silicon atom will remain fixed here. And as you vary temperature, this number will change. Number of holes, number of that one. Later on, I'll give the formulas. Okay, got the idea now? So vacancy created by valence electron. This is a very difficult concept for you because you started from positive, negative charge. I said this is a positive charge. What is a hole? Hole is a positive charge. It will also propagate. It will have mobility. It will possess positive charge. It will possess mobility. What do you mean by mobility? This electron, so inside what will happen? Electrons can, if electron is here, no, this electron can propagate here. And the hole will start moving towards right here. Later on, I'll give some examples. So this what happens practically here. So therefore now, as I decrease temperature, then as I decrease temperature, the same semiconductor will behave like an insulator. Means at absolute zero, the same semiconductor will become like an insulator. Insulator in sense, what is insulator? Not like an energy gap I increase, no. Empty conduction band. That's called like insulator. So if I decrease temperature, what happen? We'll get almost empty conduction band. So it's like an insulator. So at absolute zero, the same semiconductor will behave like like an insulator. Then at higher temperatures, it will be like a conductor. At room temperature, it will be like a semiconductor. And this is what the material which we are using in a mobile, laptop, everywhere. What all today you say digital revolution, no, it is due to this semiconductor. So at room temperature, how do it will behave? It will behave like a insulator. At room temperature, just like semiconductor, you can put it. As you increase temperature, what will happen? Where is the band structure? As you increase temperature, more and more valence electrons will get sufficient energy and they'll jump to the conduction band. More electrons, free electrons available. Then it become like similar to conductor. As you decrease temperature, what will happen? So we don't get any holes, fully filled up valence band. At absolute zero, fully filled valence band and empty conduction band. This is nothing but to insulator, no? This will not change. Therefore, at absolute zero, the same semiconductor semiconductor, I'll write in short, semiconductor behaves as an insulator. Then at higher temperatures, behaves as a conductor. At room temperature, it will be, the material will behave like as its own semiconductor. So what we're discussing is at room temperature. Okay, fine. You can see some few free electrons, few holes. So this is the intrinsic semiconductor, what we call. So it's a pure semiconductor. So what all I discussed is This is for, let me call, this is, so what do you mean by intrinsic semiconductor in its purest form? So what is intrinsic semiconductor? Semiconductor in purest form. What is the band energy band diagram for intrinsic semiconductor? You have to show few holes and few free electrons. But sir, I'm doing this experiment at absolute zero. So usually what is the like a reference temperature we take to do all our research? 24 or 20 to 25 degrees Celsius. So at room temperature means it is 20 to 25 degrees Celsius. At 20 to 25 degrees Celsius, what is the feature of the material? That has to be taken as standard. So at room temperature, so how the intrinsic semiconductor means, you have to show like this. At absolute zero, you have to show empty conduction band. So this diagram what happen? Silicon substance at room temperature, or it is for intrinsic semiconductor. So what do you mean by intrinsic semiconductor in its purest form? It will be amorphous or crystalline. The semiconductor is in a crystalline form. Amorphous, all of you know, powder, talcum powder. That's called as amorphous. Crystalline form. Crystalline, I think if you take the sugar granule, again you put in that microscope and make it know, you can see that crystalline form. That one means where the crystal lattice structure will have some sort of a ordered way, that one. So that is called like a crystalline form. So semiconductor usually will be there in the crystalline form. A good example, silicon. Shall I say sand? If you purify that sand, nothing but you'll get silicon. Sand, you just go to the river bed. You just go to any river bed or say like a seashore, something there, no? So you can get sand, that one. That is nothing but the silicon, not in purest form. So as I purify it, then it will become a silicon intrinsic semiconductor. So it is in a crystalline form. Yes, very much. Sand, you just take it, no? It's a crystalline. Okay, this is about the theoretical band theory. Now we'll define few things here. Intrinsic carrier concentration. So this is the number of electrons per unit volume in the conduction band or the number of holes per unit volume in valence band is called as intrinsic carrier concentration. So what to do? Again, this is done at room temperature. See, you make it yourself fixed here. We are going to study everything at room temperature. The semiconductor metal is designed keeping room temperature in the mind. So here, what is intrinsic carrier concentration? How to calculate? Number of electrons. See, who will be there? Valence electron in conduction band, not possible, no? Where you can see valence electrons? In valence band. And any electron that exists in conduction band should be free electron. So this that's why I shown clear thing that black dots I should not show here. Actually, in fact, the valence electrons, it's of no use for me. That's why we don't show valence electrons in anywhere here. What I'll be showing, either the free electron in the conduction band or the holes in the valence band. So number of free electrons in the conduction band per unit volume will be the intrinsic carrier concentration, or the number of holes in the valence band per unit volume will be the intrinsic carrier. So how many holes are there? Those many free electrons should be there. Any reason? Because the valence electron which jumps from conduction band to the conduction, when it jumps from valence band to conduction band, will become free electron, no? Getting the idea? a valence electron, when it jumps from valence band to conduction band, will become free electron. Able to make it out, that condition? So therefore, if at all any electron, if I say in conduction band, it's a free electron. And any electron in valence band is valence electron. I'm not bothered to show that dots. It's of no use for me. What is used? These holes are useful. So therefore, that holes, and the vacancy created by valence electron in valence band is a hole. That I'm displaying it here. This is you can see that one everywhere. We are not bothered about these dots, black dots, because it is of no use for me. Anything useful, this hole or this particular thing. Now next again, one more thing we'll define called like a Fermi level. It is